Good day, everyone. I'm Miss J.N. Consignado, and the topic that I'm going to present is about alternating current. As it is defined, alternating current or AC is an electric current which periodically reverses direction and changes its magnitude continuously in time. So as we can see here in the GIF, unlike the alternating current, direct current or DC, the current only goes in one direction, while in the alternating current, so the current reverses in direction. For a little bit of history, so we have here Hippolyte Pixii. He is known to have created the earliest model of an alternating current electrical generator, a device which was based on Michael Faraday's principle of magnetic induction. Actually, the first AC generator was created accidentally by him, Hippolyte Pixii, while he was inventing the first dynamo in 1832. So this is the device that was created by Hippolyte Pixii. This device operated by using a hand crank to spin a magnet where the north and south poles would spin over a coil with an iron core. Every time a pole passed over the coil, a current pulse occurred and the direction of the current would change. So that is the first device created by Hippolyte Pixii. That is the start of the alternating current generator. Another one is that we have Nikola Tesla. So he made dozens of breakthroughs in the production, transmission, and application of electric power. He invented the first alternating current motor and developed AC generation and transmission technology. Nikola Tesla was a former employee of Thomas Edison, but eventually resigned in Edison's company. It is believed that Thomas Edison asked Nikola Tesla to create a machine that can distribute or transmit electricity throughout America, and in return, he will give $50,000 to Tesla. But after Tesla made the machine, Edison did not pay him. Instead, he told Tesla that it is just an American humor. With that, Tesla resigned and instead joined the company Westinghouse Electric, and then the birth of AC generation, and in which AC becomes part of transmission lines and the production of electricity. Next is how AC generator works or AC works. AC works in the principle of electromagnetic induction. In electromagnetic induction, when there is a relative motion between the coil and a magnetic field, an electric current or EMF is induced in the coil. But first, let us have the parts of this simple AC generator. For the first part, we have what we call as the armature. The armature is a rectangular coil with many turns wound around a soft iron core. The next part is the shaft. So we have the shaft so that it can be rotated rapidly. Next part is the field magnet. The field magnet with concave poles. The other part are the slip rings. The slip rings are connected to the armature and thus rotate with the armature. Next part are the brushes. It provides electrical contact with the slip rings and the load. So in this case, our load is the galvanometer. How the AC generator works. When the armature rotates between the poles of the field magnet, the magnetic flux linked with armature changes continuously. As a result, an EMF is induced in the armature. This in turn produces an electric current. As we are going to observe the load in this case in a simple AC generator, the galvanometer needle swings between the negative and positive values, which means that an alternating current is flowing through the galvanometer. As for the direction of induced current, I have here a video that shows how the direction of the induced current changes.
Of induced current. Initially, The armature ABCD is vertical with its arm AB up and CD down. The direction of magnetic field is from left to right. As the armature undergoes a half rotation clockwise, arm AB moves down while arm CD moves up. According to Fleming's right-hand rule, the current will flow in the direction DCBA. So, the current will flow from B1 to B2 through the galvanometer. Now during the next half rotation, arm AB moves up while arm CD moves down. Again by Fleming's right-hand rule, current will flow in the direction ABCD, that is, from B2 to B1 through the galvanometer. Thus, the induced current changes its direction every half rotation.
So that is how the direction of induced current changes. Next, due to the alternating negative and positive values, there are alternating current waves that are formed. So we have AC waveforms. AC can come in a number of forms as long as the voltage and current are alternating. The first type of AC waveform that we have is the sine wave. So it is the most common type of AC waveform. The AC in most homes and offices have an oscillating voltage that produces a sine wave. So to further explain about sine wave, I have here another video.
As well as showing the current flowing, the sine wave also shows how the voltage is varying. Starting at 0 and going through the complete series of changes, through 0 and back to 0 again, we say that a cycle has been completed. The time taken for a cycle is called the period. If in 1 second 4 cycles have been completed, we say the AC has a frequency of 4 cycles per second. In this case, the period, the time taken for 1 cycle, is of course a quarter of a second. And from this we can see a relationship between period and frequency. Period equals 1 over frequency. The 50-cycle AC of the British National Grid has a period of 1/50th of a second. Incidentally, instead of saying cycles per second, we use the name hertz. In the United States, all electricity is generated at 60 hertz. The AC supply in a ship is usually 60 hertz, 60 cycles per second also. So diagrams like this are often used to illustrate alternating currents and voltages. And as we heard, this particular one is called a sine wave.
So that is the sine wave. The next AC waveform that we have is the square wave. Square wave are often found in the AC that is used in digital and switching electronics to test their operation. The last AC waveform is the triangle wave. So this triangle wave is found in the AC that is useful in sound synthesis and are useful for testing linear electronics like amplifiers. So those are the 3 types of AC waveforms: sine wave, square wave, and triangle wave. Next will be about the applications of alternating current. So alternating current tends to be used for the power distribution. It has the advantage that it can easily be converted to other voltages using a simple transformer. The form of electrical energy that consumers typically use when they plug kitchen appliances, televisions, fans, and electric lamps into a wall socket are through AC. So here are the comparison for DC system and an AC system. In the illustration, both systems have 480 volts and 100 amps. In this system, the electric current passing through the transmission system, which is 1,000 feet long, is 100 amps, constantly produced directly to the load. In the AC system, there is a use of a transformer before the electric current passed through the transmission system. As it passed through, it only have 10 amps, and before supplying the load with electric current, it should again pass through a transformer. Alternating current is cheaper to generate and has fewer energy losses than direct current when transmitting electricity over long distances. So here in the illustration, it can be seen that in the DC system, as the current passed through the transmission system, it is 100 amps, while in the AC system, it's only 10 amps with the use of the transformer. What are the advantages of an alternating current power system or AC power system? Number one, it is a very flexible system. It can deliver power to loads over vast distances using transformers. And AC generators are also sturdier and easier to build than DC generators. DC generators need brushes and commutators to generate DC current. Okay, so that's all for the alternating current. These are the references for my presentation. And thank you very much for listening.